What happens when the most destructive objects in the known universe draw closer to one another? Not with explosions, not with fire, but with silence, an invisible tension stretching across the fabric of space-time itself. No sound, no light, only gravity. Two black holes spiraling toward each other in a dance that took billions of years to begin and will end in seconds. But that end, if we can even call it that, is also a new beginning. It's the moment when reality bends in ways no human can witness, but which the cosmos remembers. In deep space, far beyond the reach of any telescope, this cosmic ballet plays out. At first, the two black holes drift slowly around a common center. Orbit by orbit, they lose energy, not through friction or air resistance, but by radiating waves of gravity. These waves ripple out into the universe, distorting the geometry of everything they pass through. The black holes draw closer, the spiral tightens, and time begins to twist. At these scales, gravity stops being a gentle force. It becomes the sculptor of destiny. Each black hole carries mass greater than entire stars, compressed into a region so small, so dense, that light cannot escape. As they orbit, the distortions they create in the fabric of space grow more intense. Their gravitational fields begin to overlap, and soon, they are no longer two isolated beasts. They are entangled in a gravitational web that will not let them go. From Earth, nothing is visible. These mergers are hidden behind vast curtains of interstellar dust, darkness, and distance. But the universe is never truly silent. When black holes move, they create tremors, cosmic vibrations that ripple through the universe like the aftershock of an invisible earthquake. These are gravitational waves, and long before humanity could see black holes, it would one day learn to listen for them. Back in space, the black holes continue their dance. What began as a lazy spiral is now a furious storm. The two bodies are racing around each other at a significant fraction of the speed of light. Each orbit releases more energy than all the stars in the observable universe. Yet almost all of it goes into the distortion of space-time itself. No radiation, no glow, only warping. The closer they get, the faster they spin. A few milliseconds before collision, they're completing hundreds of revolutions per second. The structure of the surrounding space twists like a vortex. The tidal forces, the stretching and squeezing from gravity, become immense. If anything dared get close, it would be torn apart at the molecular level. And then, in the final moment, the event horizons touch. To the outside universe, nothing special seems to happen. There is no flash of light, no crack in the sky. But for the black holes themselves, this is the ultimate union. Their masses fuse, their event horizons merge. And from two singularities, if such things truly exist, emerges a new one. A single, larger black hole, more massive and more stable than either of its parents. But something is missing. The mass of the resulting black hole is not the simple sum of the two that collided. A portion is gone, vanished, not in the traditional sense, but transformed into gravitational waves, into ripples, into whispers sent across the universe. These waves travel for billions of years. They pass through galaxies, through nebulae, through clusters and voids. They do not scatter. They do not fade like light. Instead, they carry the signature of that final dance, its rhythm, its weight, its violence. They carry the memory. When they finally arrive at Earth, they are unimaginably faint. The strongest wave might change the distance between 2 points by less than the width of a proton. But that is enough. Because in 2015, for the first time in history, we had built something that could hear them. It was called LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO was not a telescope. It did not capture images or reflect light. It was an ear pressed to the floor of the universe. And on September 14, 2015, it heard something. A chirp, not a scream, not a roar. A rising tone that lasted just 0.2 of a second. But that chirp told the story of two black holes, each about 30 times the mass of our sun, colliding over 1 billion light-years away. The signal was tiny, but the implications were vast. For the first time, we didn't just infer black holes from their gravitational effects on stars. We didn't just imagine them based on equations. We heard them move. We recorded the sound of invisible objects crashing into one another and confirmed that Einstein's predictions, made a century earlier, were correct. Space-time could vibrate, and we could feel it. More detections followed, each one a note in a cosmic symphony billions of years in the making. Some involved black holes of unprecedented mass. Others hinted at neutron stars or strange intermediate systems. But all of them pointed to one truth. The universe is full of collisions. Violent, unseen, but no longer silent. What happens when two black holes collide? In one sense, almost nothing. They merge. The result is still black, still silent, still hidden. But in another sense, everything changes. The merger sends out messages. Gravitational waves carry the news across the cosmos. The final moments of the dance encode the mass, the spin, the distance of the black holes. From those faint ripples, we can reconstruct a story that ended before life on Earth had even begun. And in those stories, we glimpse something else. We see how black holes grow, not just by swallowing matter, but by merging with each other. We see how galaxies form and evolve, how structure emerges from chaos. Each collision is a fossil, a record of how the universe built itself, piece by invisible piece. We also encounter puzzles. Some black holes are too massive to have formed from stars, yet not massive enough to be called supermassive. How did they form? Are they primordial, leftovers from the Big Bang itself? Or are they the product of multiple mergers, stair-stepping their way up the cosmic mass ladder? And what about the spin? When two black holes merge, their individual spins combine, but not always in obvious ways. Sometimes the result spins wildly. Sometimes it barely turns. These outcomes hint at the environments in which the mergers took place: dense stellar clusters, chaotic galactic cores, or perhaps quiet binary systems evolving in isolation. Each detection is a clue, each waveform a message, and as we collect more, the picture sharpens. But the most profound consequence of black hole mergers is not astrophysical. It is philosophical. When we witness these collisions, when we hear them, we are not just learning about space. We are learning about time, about fate, about the boundary between determinism and chaos. We are watching the universe change itself, and we are beginning to realize that the quietest moments can be the loudest, that the darkest places can shine brightest, not in light, but in meaning. That black holes, long thought to be dead ends, are the loudest voices in the cosmic choir, and their song is only just beginning. Once the collision is complete and a new black hole is formed, the universe doesn't immediately move on. Instead, something strange happens, something that scientists didn't expect at first, but which now provides even deeper insight into how space and time behave under the most extreme conditions. The newly merged black hole doesn't settle instantly. It quivers. It rings. Like a struck bell, the newborn black hole resonates with the energy of the merger. It sends out gravitational waves in a diminishing pattern known as the ring down. This phase of the process is crucial because it carries the purest signature of the black hole's new state: its mass, its spin, and its shape. And that shape, surprisingly, is not static. The ring down allows physicists to test the no-hair theorem, a prediction in general relativity that all black holes are completely defined by just three properties: mass, spin, and electric charge. All other information about what formed the black hole, whether it was made of gas, rock, or stars, is lost. But during the ring down, small deviations might appear. Irregularities in the gravitational waves could hint that black holes are not as simple as Einstein thought. So far, the theory holds. The signals we've observed match predictions nearly perfectly, but physicists remain alert. Any anomaly, any unexpected oscillation, could signal new physics, perhaps even the long-sought quantum gravity. And that's where things get even more intriguing. You see, black holes aren't just massive, they're mysterious. And when they collide, they don't simply make a larger hole. They make a puzzle, a paradox. And nowhere is this more evident than in the problem of information. From the outside, black holes seem like perfect absorbers. Anything that crosses the event horizon is lost forever. But according to quantum mechanics, that can't be true. Information, the quantum details of every atom and particle, must be preserved. So when two black holes merge, each one having swallowed untold volumes of matter and light, where does all that information go? If it disappears forever, then one of the most fundamental laws of physics breaks down. If it doesn't disappear, then we must explain how it is preserved. despite being trapped behind an event horizon that, by definition, doesn't allow anything to escape. This is the black hole information paradox, and it becomes even more intense after a merger. Because when two black holes become one, the event horizon changes. The surface area increases. The internal volume, whatever that even means in a black hole, may shift dramatically. And with these changes come questions. Did the information from each original black hole combine? Did it remain distinct? Or was it scrambled so thoroughly that it's now encoded on the new event horizon, in a pattern we have yet to decipher? Some physicists suggest that the information is preserved on the horizon's surface, thanks to a principle known as holography. Others propose that the process of Hawking radiation, which slowly causes black holes to evaporate, may release that information back into the universe over unimaginable timescales. Still, others wonder whether the very concept of information inside a black hole is flawed, that perhaps the interior doesn't exist in the way we think. But here's the twist. Black hole mergers might help us find the answer. By studying the gravitational waves emitted before, during, and after collisions, we can look for subtle clues. Variations in waveforms, delays in ring-down, unexpected harmonics. These could point to deviations from general relativity, deviations that hint at how information behaves near and within black holes. In one bold proposal, researchers suggest that black hole mergers could produce echoes, faint ripples in space-time that arrive milliseconds after the main gravitational wave. These echoes, if confirmed, would suggest that the event horizon is not a smooth, featureless surface, but something more complex. Something that reflects information. Something quantum. So far, no definitive echoes have been detected, but the search continues. Because the reward, unifying general relativity and quantum mechanics, is the holy grail of modern physics. Meanwhile, black hole mergers continue to surprise. In 2020, the LIGO and Virgo observatories detected a merger that stunned scientists. Two black holes, one weighing 85 solar masses and the other 66, collided to form a black hole of 142 solar masses, the first direct observation of an intermediate mass black hole. This was unexpected. Previous models suggested that black holes in the 60 to 120 solar mass range couldn't form from stellar collapse. Stars that massive were thought to undergo a different process, pair instability supernovae, which completely disrupt the star and leave no remnant behind. So where did this black hole come from? The answer, once again, may be mergers. Perhaps smaller black holes merged again and again in dense stellar environments, creating a new population of heavier black holes. Or perhaps something else is at work, something beyond current models. This discovery reshaped our understanding of stellar evolution and opened up a new branch of black hole astrophysics. But the surprises didn't stop there. Another collision showed asymmetry. One black hole was significantly larger than the other. The resulting merger kicked the new black hole away from its original location at high speeds. In theory, such recoil kicks could be strong enough to eject black holes from galaxies entirely, sending them drifting alone through intergalactic space. Imagine that, black holes born from violent collisions, then flung into the void, ghosts with no home, carrying with them the secrets of stars and systems long gone. These rogue black holes might one day be detectable, not through light, but through their subtle gravitational influence on nearby matter. Or perhaps through future instruments capable of sensing faint background ripples from ancient collisions. As gravitational wave astronomy advances, our ability to detect and interpret black hole mergers will only grow. New observatories, such as the upcoming LISA mission, Laser Interferometer Space Antenna, will operate in space, sensitive to longer wavelengths than ground-based detectors. LISA will allow us to hear mergers of supermassive black holes, behemoths with millions of solar masses, lurking at the centers of galaxies. These mergers, unlike their stellar mass cousins, shape the architecture of the cosmos itself. Galaxies collide. Their central black holes spiral toward each other. And when they merge, they send gravitational tsunamis across the universe. These waves can last for weeks, even months, telling a story of slow, inevitable union on scales almost too vast to imagine. By the time LISA launches, we may already be tracking potential supermassive black black-hole mergers using data from telescopes like Gaia or the James Webb Space Telescope. And when gravitational waves and electromagnetic signals are combined, a new era of multi-messenger astronomy will dawn. We will not just listen, we will watch, and we will begin to answer questions that have haunted physics for a century. What is a black hole, really? Is it a place? A surface? A process? What happens to information inside it? And when two black holes merge, do they simply become one? Or do they reveal something deeper about the nature of time, gravity, and the structure of the universe itself? The answers are out there, in the ripples, in the silence, in the collisions that bend the very laws of reality. When two black holes collide, they don't just combine their mass, they reshape the very geometry of space and time around them. It's a transformation not just of size, but of identity. The resulting black hole is not a simple sum of its parts. It is a new object, with new properties, and with it comes a cascade of cosmic consequences, some of which may ripple through the universe for billions of years. But to truly understand what happens next, we need to step beyond gravitational waves and classical descriptions. We must dive deeper, into realms where space becomes granular, time becomes uncertain, and the laws we thought were absolute begin to dissolve. Here, the questions turn philosophical, and the physics turns quantum. Let's begin with a foundational problem. What exactly is the interior of a black hole? From a distance, we define a black hole by its event horizon, the boundary beyond which no light escapes. But what lies beyond that veil remains unknowable, not just practically but theoretically. Once something crosses the horizon, it is causally disconnected from the rest of the universe. We cannot see it, measure it, or send a message to retrieve it. And yet, paradoxically, black holes have entropy. Entropy is a measure of information, the number of microscopic states that correspond to a macroscopic appearance. When Stephen Hawking and Jacob Bekenstein worked out the thermodynamic properties of black holes in the 1970s, they found that a black hole's entropy is not proportional to its volume, but to its surface area. That is, the number of bits of information inside a black hole seems to scale with the size of its event horizon, not its inner contents. This was the first hint of something strange. Perhaps black holes don't contain information at all. Perhaps they are information. Perhaps the event horizon isn't just a boundary, but a ledger, an encoding surface that keeps track of everything that has fallen in. And this insight leads directly into the most radical hypothesis of all, the holographic principle. The holographic principle proposes that everything occurring within a volume of space can be described by information encoded on its boundary. Like a hologram, which appears three-dimensional but is generated from a two-dimensional surface, a region of space might only appear to contain depth and volume. In reality, it could be a projection, an illusion woven from quantum bits along its edge. Applied to black holes, this means the interior may not be a place at all. It may be an emergent concept, generated by the relationships between bits of information stored on the event horizon. When two black holes merge, their horizons also merge. Their informational surfaces unite, and in doing so, they may rewrite the way we think about memory, identity, and the very fabric of space. What's even stranger, this idea doesn't stop at black holes. If the holographic principle is true, it could apply to the entire universe. Our cosmos, seemingly vast and filled with stars, galaxies, and dark voids, might itself be the projection of a more fundamental layer of reality, a boundary where the true physics resides. The entire universe might be a kind of black hole, or at least governed by the same rules. This possibility reshapes the stakes of black hole collisions. These events are no longer isolated phenomena. They're experiments conducted by nature at the frontier of reality. Each merger isn't just a gravitational outburst. It's a glimpse into the operating system of the cosmos. And what about time? In most physics equations, time is reversible. The laws that govern particles and fields work the same forward or backward. But in thermodynamics, and in our experience of reality, time flows in one direction, from past to future. Black hole collisions may hold clues to this mystery as well. When two black holes merge, the entropy increases. The new event horizon has a larger surface area, and thus a greater capacity for information. This is consistent with the second law of thermodynamics, that entropy never decreases. But what if this isn't just a consequence? What if it's a cause? Some theorists suggest that the arrow of time, the reason we perceive a past and a future, emerges from processes like black hole mergers, that the growth of entropy, especially in systems that reshape space itself, defines time's flow. In this view, time doesn't exist independently. It arises from the entanglement of information across horizons. This means every black hole collision isn't just a cosmic smash. It's a tick of the universe's clock. And in this ticking, we might find another layer of mystery, the nature of quantum entanglement. In quantum mechanics, entangled particles share information instantaneously, no matter how far apart they are. This phenomenon puzzled even Einstein, who called it spooky action at a distance. But in modern physics, entanglement is no longer fringe. It's central. Some physicists propose that space itself is built from entanglement, that the distances we measure and the dimensions we perceive are the large-scale consequences of quantum connections. When black holes merge, their entangled states combine. This process may not just create a new black hole. It may momentarily alter the web of entanglement that defines the structure of space-time in the surrounding region. In effect, black hole mergers might be editing the blueprint of the universe, stitching new threads into the quantum fabric. And then, there is the most speculative idea of all: black holes as quantum computers. If a black hole stores information on its surface and processes that information as it absorbs matter and emits radiation, then it may function as a computational system. Not a classical one, like your laptop, but a quantum computer operating on qubits, manipulating entangled states, and encoding the history of its interactions. When two such quantum processors merge, the result is not just a larger database. It's a new machine with new capabilities. The computation continues, but now with a broader dataset, more memory, and perhaps more complex algorithms. Some physicists have begun to model black hole mergers as quantum gate operations, fundamental steps in quantum computation. In this view, the universe isn't just made of information. It is processing information. It is a computation unfolding across time. This idea, once dismissed as metaphysics, is gaining traction, and black hole mergers, with their measurable gravitational waves and precise timing, may provide testable predictions for these bold theories. Still, not all questions can be answered from a distance. To truly understand what happens inside the horizon, to witness the fusion of singularities, the blending of entropy, the remixing of information, we would need to fall in ourselves. But we cannot. Even in thought experiments, the interior remains elusive. It shifts with the observer. It defies simple mapping. And perhaps that's the point. Perhaps black holes don't hide their secrets. They are their secrets. Every merger, every wave, every new horizon is a line in the story, a phrase in the cosmic code. And we, from our perch billions of light years away, are only beginning to read. There's a paradox at the heart of every black hole. When two of them collide, that paradox becomes amplified, etched into the structure of space-time itself. It's not just about mass, energy, or gravity anymore. It's about the nature of information, the laws of physics, and the question that keeps physicists awake at night. Can the universe truly erase? Let's rewind to the moment just after the collision. The two black holes have merged. Gravitational waves have rippled outward. A larger, spinning black hole now dominates the region, a new behemoth formed from the wreckage of collapse. To the outside observer, it seems simple: energy in, energy out. Mass has increased, entropy has risen. The second law of thermodynamics has been satisfied. But something doesn't add up. All the particles, light, dust, and radiation that once orbited the two separate black holes are now gone. They've been swallowed. And so, too, have their histories, the intricate quantum states that define their exact configurations. According to general relativity, this information is now sealed behind the event horizon, inaccessible forever. But according to quantum mechanics, that can't happen. In the quantum world, information cannot be destroyed. This isn't a philosophical position. It's a rule, one of the most fundamental. If a particle changes state or a system evolves, it must do so in a way that allows the process to be reversed, at least in principle. No information can simply vanish. And that's where the black hole information paradox arises. Because if black holes trap information permanently, then the laws of quantum mechanics are broken. But if the information somehow escapes, then general relativity is incomplete. Two pillars of modern physics, both experimentally verified, are now in direct contradiction. And that contradiction only intensifies when black holes merge. Think of it like this. If a black hole is a cosmic vault, then two merging black holes are two vaults combining. Where does all that encoded information go? Does it blend perfectly? Does it stay intact? Does some get lost in the process? Or is the new event horizon simply a new encoding surface? One that somehow remembers the detailed past of everything it has absorbed? The stakes are enormous. If information is truly lost during a black hole collision, then the universe is not a deterministic machine. It is an eraser, a forgetter, a destroyer of memory. But if information is preserved, hidden somehow in the ripples of space-time, or smeared across the new horizon, then we need a new framework for understanding gravity. One that respects both Einstein's curves and the uncertainty of quantum fields. This is where string theory and the holographic principle enter the story again. Some physicists argue that the information from the two original black holes is never truly inside. It's encoded on their event horizons, thin, two-dimensional surfaces surrounding their invisible interiors. When the black holes merge, their horizons merge too. And the information is preserved, not in a hidden volume, but on a new, unified surface. This idea finds support in a surprising place: black hole thermodynamics. Bekenstein and Hawking showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This suggests that the amount of information a black hole can contain is determined by its surface, not its interior. And when two black holes merge, the surface area of the new horizon is larger than the sum of the two originals. More area, more entropy, more information capacity. But what exactly is being encoded? Some physicists believe the surface holds quantum microstates, tiny configurations that represent different possible histories. Others argue for entanglement patterns, mathematical correlations that preserve relationships without specifying exact locations. Either way, the message is clear. The event horizon is not just a boundary. It's an interface, a dynamic membrane where the physics of gravity and the physics of information collide. This brings us to one of the most controversial ideas in modern physics, the firewall paradox. In 2012, a group of physicists proposed a shocking possibility. To resolve the conflict between quantum mechanics and general relativity, they suggested that the event horizon might not be smooth. Instead, it might be a wall of searing radiation, a firewall that vaporizes anything attempting to cross. The logic is subtle but profound. When a black hole emits Hawking radiation, it does so by creating pairs of virtual particles near the horizon. One falls in, the other escapes. These particles are entangled, linked in a quantum way. But as more and more particles escape, something strange happens. In order to preserve quantum consistency, the outgoing particles must remain entangled with the earlier radiation. But they're also supposed to be entangled with their partners inside the black hole. And that's a problem. Quantum systems can't be maximally entangled with two other systems at once. It's like trying to share an unbreakable secret with two people at the same time. It doesn't work. Something has to give. If the entanglement with the inside is broken, then the horizon becomes a place of violent quantum disruption, a firewall. This idea sent shockwaves through the physics community, because if true, it means the most fundamental assumption of relativity, the equivalence principle, is violated. According to Einstein, you should feel nothing special as you cross the horizon. But if there's a firewall, you're incinerated. It's a paradox that cuts to the heart of black hole mergers. If firewalls exist, then the point of collision between two black holes is not just a smooth transition. It's an eruption, a quantum catastrophe where space-time breaks down entirely. Some physicists reject the firewall idea. Others embrace it. Still others look for a third path, one that rewrites the rules of entanglement or introduces new layers of space-time structure. One such proposal is ER equals EPR. This elegant idea suggests that entangled particles are connected by tiny wormholes, Einstein-Rosen bridges. That entanglement and geometry are two sides of the same coin. In this view, the smoothness of space-time is maintained because the entanglement that gives rise to it is distributed in subtle, hidden ways. Black hole mergers, then, become mergers not just of mass and energy, but of entangled geometry. Their event horizons blend, their entanglement networks reconfigure, and the result is a new patch of space-time, one that remembers everything but reveals nothing. Still, no one knows for sure. We haven't yet decoded the gravitational waves from black hole collisions well enough to see if they carry subtle information signatures. We haven't detected Hawking radiation directly. We haven't unified quantum mechanics and gravity. But we're trying. The LIGO and Virgo observatories have already detected dozens of black hole mergers. Each one is a message from the edge of physics. Each one is a data point in the greatest mystery of all. And with every detection, we get closer to understanding how information flows in the universe, closer to resolving the contradictions between our theories, closer to knowing whether black holes forget or remember. In that sense, black hole mergers are not just astronomical events. They are philosophical experiments. They force us to ask, what is real? What is knowable? What happens to a particle, a photon, a memory when it falls into the dark? And maybe, just maybe, the answers lie not inside the black hole, but on its surface. Not in what is lost, but in what remains. Because even when everything else vanishes, the questions persist. Long after the gravitational waves have faded and the cosmos has returned to silence, the collision of black holes continues to echo, not in sound, but in thought. What happens when two black holes collide is more than an astrophysical event. It's a challenge, a riddle left at the doorstep of our deepest scientific theories. And its answer may reshape how we view the very fabric of reality. Let us turn to the concept of a Planck scale transition. Named after Max Planck, the Planck scale refers to the realm of the very, very small, distances and times so short, energy levels so extreme, that classical physics simply ceases to work. It is at this scale, far beyond the reach of current experiments, that the effects of quantum gravity are expected to emerge. When two black holes merge, the central region, known as the neck or throat of the merger, briefly compresses into a state of extraordinary density. Not infinite, but close enough to the Planck scale that quantum gravitational effects could dominate. This is the edge of knowledge, where no human theory fully applies. What happens there? No one knows for certain, but there are hints. Some physicists propose the birth of a Planck star, a hypothetical compact object that halts gravitational collapse via quantum pressure. In this scenario, instead of collapsing into a singularity, the combined core of the two black holes bounces, like a spring compressed beyond its limit. The event horizon still forms. The structure remains hidden, but inside, something different unfolds, something more dynamic than the static point of infinite density we've long imagined. This idea is compelling not just for its mathematical elegance, but because it avoids the singularity problem entirely. No infinities, no broken equations, just extreme states of matter governed by laws we are only beginning to glimpse. Another possibility lies in loop quantum gravity, a framework that attempts to quantize space-time itself. In this theory, space is not continuous, but made of discrete loops, tiny, granular units woven into a cosmic lattice. At everyday scales, this fabric appears smooth, like water viewed from a distance. But at the Planck scale, the granularity becomes undeniable. During a black hole merger, space-time may ripple not just in waves, but in knots. Quantum loops could twist and reconnect, forming new topologies, spaces with holes, bridges, or even closed loops in time. If such structures exist, they could encode vast amounts of information in ways we have not yet imagined. And then, there's the most radical idea of all, that when two black holes merge, they don't just create a larger black hole, they create a new region of reality. A patch of space-time with its own laws, its own constants, its own arrow of time. A bubble of physics born from the violent fusion of curvature and entropy. This is the idea of black hole cosmogenesis, that each black hole is a potential seed for a new universe. It's a stunning hypothesis, one that suggests our own universe may have been born from a black hole in another, parent universe. In this view, black holes are not just endpoints, but wombs, cosmic incubators that gestate new realities. If true, this would imply that the multiverse is not a distant abstraction, but a natural outcome of gravitational evolution. Every black hole merger could represent a branching point in the tree of existence. Not metaphorically, literally, but what about from our perspective? From Earth, from our detectors, from our equations, we still only see shadows. LIGO records a momentary chirp, a burst of gravitational waves, rising and falling like a heartbeat. That's all. No images, no radiation, just the deformation of space itself. And yet, in those waves lies encoded the history of the merger, the masses, the spins, the angle of collision. Like forensic scientists, we reconstruct the scene from these subtle clues. But what if more is hidden in the waveform? Recent research suggests that gravitational waves might carry quantum imprints, tiny deviations from classical predictions, arising from the exotic physics of the merger's core. If we could detect these imprints, we might unlock a new observational window into quantum gravity. Future observatories, like the space-based LISA Laser Interferometer Space Antenna, are being designed with this goal in mind. With their increased sensitivity and longer baselines, they could detect mergers millions of light years away and resolve fine details we've never seen before. Imagine this. A black hole merger occurs in a galaxy far beyond the Milky Way. LISA detects the chirp, but this time, embedded within the waveform, scientists find something new, an unexplained resonance, a second signal, a whisper of quantum structure. Suddenly, we're no longer blind to the merger's interior. We're beginning to hear its secrets. But what about the philosophical implications? If black hole mergers reshape space-time, encode information on horizons, possibly birth new universes, then what does that say about us? About consciousness? About identity? About permanence? It's tempting to see ourselves as distant observers, removed from these colossal events. But in a cosmic sense, we're not. The atoms in your body were forged in stars. The gravity that holds your feet to the floor is the same force that governs black hole mergers. The physics is universal. And if black holes store information on their surfaces, could the universe itself do the same? Could our own reality be a kind of hologram? A vast projection encoded on a cosmic boundary we cannot see? This is the question that haunts the frontier of physics. Not just what happens when two black holes collide, but what does that collision tell us about everything? Because every merger is a paradox in motion. Every chirp is a cry from the edge. And every question we ask brings us closer, not to answers, perhaps, but to understanding. And so we return, finally, to the collision itself. Two ancient giants spiral inward, locked in a fatal embrace. Their orbits decay. Their event horizons stretch and distort. Time slows. Tides rise. And then, impact. Space ripples. Matter vanishes. Horizons blend. And in that moment, silent, invisible, unstoppable, a new question is born. A question not of gravity or entropy or quantum fire, but of perception. Because when we ask what happens at the heart of a black hole merger, we're not just probing a distant phenomenon. We're testing the limits of thought. We're standing on the edge of what can be known and staring into the dark. Now the story quiets. The cosmic collision is complete. The waves have traveled. The echoes have faded. And yet, somewhere far away, those black holes, now one, continue to spin in silence. In the stillness that follows, a realization settles. Black holes aren't monsters. They're mirrors. They reflect not light, but ignorance. The edge of what we know becomes the shape of what we fear. But in trying to understand them, in building instruments, equations, and dreams, we also reshape ourselves. Perhaps that's the true gift of these titanic collisions. Not just the knowledge of gravity, or entropy, or time, but the invitation to wonder, to imagine other laws, other realms, other beginnings. To admit that even the darkest parts of the universe are not empty. They are full of secrets, waiting to be understood. Full of patterns, waiting to be seen. Full of meanings, waiting to be made. And in the soft hum of space, long after the stars have blinked away, that curiosity remains. Black holes collide. Galaxies drift. Universes may be born. But wonder? Wonder endures.